So in this particular circuit configuration, we're looking at what's called a parallel circuit. And as you can see by the picture, we have a 240 volt alternating current source. Doesn't matter if it's alternating or direct. In the case of resistors, the current and voltage all treats the resistance in the same way. But it's in a parallel configuration. The difference between a series circuit and a parallel circuit is that a parallel circuit has more than one path through which the current can flow. So, for example, if there was a switch here or there was a break in the circuit, there are still two alternative paths through which this current can flow. And that being said, as this thing is configured right now, the current will be passing through each one of these resistors. We have the 120 ohm, 45 ohm, and 360 ohm in such a proportion that the greatest current will go through the lowest resistance. So I guess qualitatively we could say that the 45 ohm resistor should see the most current, and likewise R3, which is the 360 ohm resistor, should see the least amount of current since it has the greatest resistance. But the proportion by which each of those currents are ran through each resistor is a function of how parallel circuits sort of behave. We talk about voltage as being like electrical potential difference, and voltage, is sort of like how much electrical potential energy a circuit may have per the amount of charge available to do what it does in a circuit, per the amount of charge for it to move around. That being said, the rule for a parallel circuit, is that the voltage across each branch of a parallel circuit is the same. In a series circuit, the rule was, hey, the current is the same throughout and the voltages add up. In this case, with a parallel, the voltage across each of these branches between R1, R2, and R3 are all respectively, in this case, 240 volts. And then it's the current that adds up, because as the current travels through this segment of wire, it reaches this node or this point in the circuit where there's a split. A proportion of it travels through R1, while the difference then continues on down the line, and a portion of it will then pass through R2, and the remainder then would pass through, the last resistor R3, before they all come back, if you're following my mouse on the screen, before they all come back to this node or this point where there's a junction of wires, so to speak, in the circuit. When the current reaches this node, all of the currents add to the total current in the circuit. It's that fact coupled with the voltages being dropped across each loop, each segment of the parallel circuit, that will show us that the equivalent resistance cannot be found just by adding up all the values of the resistor. So we cannot add 120 ohms to 45 ohms to 360 ohms, much like we did with the previous circuit. In this case, the shorthand way to calculate equivalent resistance in a parallel circuit, well, we'll just write out the equation here and we'll make sense of it in a moment. The equivalent resistance, Req, is equal to the inverse of the sum of the inverses. All right, let me write this out and then explain what it is I'm trying to say. So in order to find the equivalent resistance, we would have to take 1 divided by 120 plus 1 divided by 45, which is R2, plus 1 divided by 360, which is R3, get those respective decimal equivalents, and then take the inverse of that value down here to figure out what our resistance is going to be. That being said, the resistance in a parallel circuit is always less than the equivalent resistance for a given branch. In this case, this is strictly a parallel circuit configuration, not a series parallel combination, but strictly a parallel configuration. So if this was 120 ohms and this is 40, the middle one is 45 and the last is 360 as we had established, we will note there to be a resistance of probably an equivalent resistance, probably less, at the very best case, it is less than half of the 45 ohm resistance due to the way this works out. What I'm going to prove to you, what I'm going to show you today then is how to use this equation very quickly, calculate the total current using, Ohm's law, V divided by R gives me I, and then go through and calculate each of the respective currents, which should then add up to our already predetermined total current using Ohm's law to verify that this is in fact what it is. So I'll just write out the equivalent resistance process here so you can see what I'm talking about. So 1 over 120 plus 1 over 45 plus 1 over 360. And if you're going to mess anything up, it's that in going through this process, you forget to take the inverse of your final answer. Okay, so if I were to just strictly take 1 divided by 120 plus 1 divided by 45 plus 1 divided by 360, I end up with 1 over 0.033. That's not my answer. I need to take the inverse of that. So in further reducing this thing down, I end up with 30 ohms. Okay, so perhaps I was a bit off in my original estimation here, but in either case, we do find the equivalent resistance to be we find it to be less. Let's just say that. We find it to be less than the smallest resistance value that we have. You will never have an equivalent resistance be any larger than the smallest value you're given. Now, if we accept this as the true equivalent resistance of the circuit, in manipulating Ohm's law, which says change in voltage over resistance gives me current based off of V equals I times R, and we take 240 divided by 30, 240 volts divided by 30 ohms, barring math failing me at this point, we end up with 3 amps. That is the total current in the circuit. So I will maybe highlight this. So as each of the currents pass down through the respective branches, when they all recombine or before they split up, the total current should equal 8 amps. Okay, that's what this tells us. So now in going through and maybe verifying this, we can find the current as it passes just across the first resistor, again by applying Ohm's law, V over R. Well, the rule says in a parallel configuration, the voltage dropped across any given branch is the same. Well, in doing this rough math, we end up with 2 amps passing down the first branch. The second branch, we do the same thing, 240 volts divided by 45 ohms, and a quick calculation will yield a current of 5.3 amps. Okay, the difference between the sum of 2 and 5.3 should be I'm sorry, the difference between the total current and our present value of 2 amps and 5.3 amps should give us what's left in R3, and if I'm making a prediction there, it's probably going to be 0.7 amps, but let's figure it out. As we had maybe alluded to earlier, we should expect the smallest current in the across the third resistor because it is the smallest resistance. It's the largest resistance of the bunch. So delta V over R, keeping consistent. So 240 over 360, and you can see that's some familiar proportion of about 2/3. So we take 240 just for the sake of doing this, divided by 360, and we do in fact get 0.67 amps, which when we add all of this stuff up to what we have, you get you know, in my calculator says 7.9667, so repeating, which is basically 8 amps. So what have we done? What have we accomplished? Well, by showing you the equivalent resistance is 30 ohms, we made an estimation, or we determined using Ohm's law on the assumption that the equivalent resistance is true, what the total current should be. And we verified that by just applying Ohm's law on each branch, knowing and understanding that the total voltage of 240 volts is dropped across each branch, and taking that divided by the current resistance in each branch, we found the individual currents passing through each branch, smaller resistance, lending itself to larger currents. Larger resistances would then have smaller electrical currents passing through them. And if we were to add this all up to verify, we get a value which is very close to the 8 amps we had predicted to be true in this case. So there's just a couple different ways we can analyze a parallel circuit to determine what the total resistance is. If we had more resistors, we would have more terms in the denominator. So it'd be 1 over this inverse of 1 over plus R1, 1 over R2 plus 1 over R3 plus maybe it's 1 over R4 plus 1 over R5, so on down the line. You just keep adding the number of terms to the denominator of the parallel circuit configuration that you're given for every set of resistors that you have beyond that. For a series parallel combination, we will combine techniques of both a series circuit with that of a parallel circuit to eventually basically come up with the exact same thing. But just keep in mind that what we talk about in each one of these respective videos can be then used to determine the result of a more complicated circuit. Thanks for watching.